Hi and welcome to this, my first video in a series of videos on definite integration. So these videos are a follow-up to our videos on integration and how we integrate functions to get back to derived functions. And also, before this video, it might be worth having a look at the Trapezoidal Rule videos. So here's our success criteria and learning goals, and of course the resources for the textbook that we use. Let's move on. So we're going to talk about finding the exact area under a curve. And to calculate the exact area under a curve, this is where we use definite integration. So let's imagine we had a question where we wanted to find this orange area. Y equals f of x is our curve. Looks a bit cubic, but it could be anything. And our boundaries, which are called terminals, are a and b. Now, often a and b will be nice easy numbers, 0 and 2 or something like that. But it could be anything. And we've seen this set up with trapezoidal rule. So what if, to find this area between A and B, we actually applied the trapezoidal rule for a whole bunch of tiny little trapeziums like this? Just little ones. Okay, in fact, what if we did it for an infinite number of them? And the width, this little bit here, is so small, it's infinitely small, and there's an infinite number of trapeziums. Well, that would lead us towards definite integration. Now, obviously, for us, with human working, it's impossible to do an infinite number of trapeziums, but theoretically, we've developed a way to do this, and it's definite integration. So, let's have a look at some notation and then a quick example. So, in our notation, you'll note here that we have a few things. First of all, this little integral sign, which hopefully you're used to by now. And then we also have our terminal. B is our upper terminal and A is our lower terminal, and they go in that order, otherwise you'll get a negative answer to what you expect. We integrate our function f of x, and of course we always make sure that we're integrating with respect to another variable. Usually this is obvious, but if you get a bit further in math you'll find multivariate calculus can throw that up in the air a bit. And then that will give us the exact area. And this is a really good method. Don't forget that sometimes we can't integrate a function. So we're going to have to go back to the trapezoidal rule and other things like it at times. But for integratable functions, this is a really good method. So let's have a look at example 1. So in example 1, we're asked to calculate the integral between 2 and 1 of x squared dx. I've chosen a nice simple function, and you can see on the diagram that we're looking for this shaded region in here. So this shouldn't be too hard. But what I'm going to do now is I'm going to set up the procedure. So I'm not going to go into a lot of detail about why. We'll build the y a little bit later on, but for now I'm setting up the procedure for finding this definite integral. So basically what I'm going to do is I'm going to calculate the integral of x squared, and that is x cubed over 3. But to determine the area between two terminals, I'm actually going to use this notation. There's a couple of similar notations you might see. I'm going to find the area below by calculating that value for each of the terminals. But we also look for a difference. So we're looking at the difference between what's here and what's here to calculate what's in between. So we have 2 cubed over 3 minus 1 cubed over 3. So all I've done is I've taken the x out and I've substituted 2 in. And this is equal to 8 over 3 minus 1 over 3, which is equal to 7 over 3. Now often my students will count the number of times that I forget plus c, so I should definitely backtrack into this question and add my plus c's. If I add a plus c here, well that will mean I've got a plus c here and a plus c here. And of course if I've got a plus c there and a plus c there, I'll have a plus c here, but I'll have a plus c inside the minus sign, and the plus c and the eventual minus c will cancel out. So actually, as it turns out, we don't need a plus c. And you're going to find now that I just ignore the plus c from now on, which you're able to do as well. If it's a definite integral question, there is not a plus c that we have to worry about. And of course, it is an area, so we write this as units squared. And it's important here to note the difference between definite integration, which is just the mathematical evaluation of this integral, and finding an area. And that means we have to apply a unit squared. And the difference will be much more important later on when the definite integral and the areas do split a little bit. What's important when doing these questions is to see that there is some indication of area. There it is here. This question had an area indicated. If there's some indication of area, then we should add our u squared. So that's the procedure, and let's run through that procedure very quickly on our calculator, because the calculator cannot do an integral for you, but it can do a definite integral between two terminals, and here it is. So here's our calculator. It's a little bit small. I'll just quickly change our view and make it a bit larger. Okay, so here's our calculator. I go into the Run Matrix screen. It's the main screen, and I've been playing with some matrices there, and I select Math F4. Then I have to scroll across F6, and then I can do an integral. But I'll only do a definite integral, as we say. So I'm going to choose my x and square it, and then I'm going to go to my terminal values and put between 1 and 2, and then press execute. And it will calculate that for me as 7/3, which is exactly what we got earlier. So we're quite happy with that result. So that's the end of our first video, an example to show you the procedure and a bit of information about how definite integral can find an exact area for you. In the second video, we're going to look at a couple more examples. Thank you.